Hello, AP Physics students. Sorry I can't be with you today. The sickness developed into a fever, so I'm not going to come share this flu with you. But I didn't want you to fall behind, so I'm giving you your notes on our new lesson. We're starting Unit 7 on simple harmonic motion. Let me go ahead and get started with that so we can jump right in. You can see that I'd like you to go grab a small whiteboard real quick. You're going to be doing some calculations and solving some different problems, and so I'd like you to have that ready, or some scrap paper and a calculator. So gather those materials for a minute. All right. Hopefully you've had a chance to do that. I might have cut you short, but let's just jump in here. You can see on the agenda, I'm going to give you some intro notes to simple harmonic motion, often abbreviated SHM, just like uniform circular motion was often abbreviated UCM, and you're going to see a lot of overlap between that unit and this unit. We're also going to hopefully have time at the end to do a little bit of a pre-lab discussion, just getting you started thinking about the spring pendulum lab we're going to try to do tomorrow on Wednesday. I hope I'll be back Wednesday without any symptoms. So let me go ahead and get rid of my ugly mug here, and then we'll jump in. All right, so oscillations is a word you often see used when we're talking about things that have simple harmonic motion. And we're going to be looking at the restoring force of springs using Hooke's law. That's all review from Unit 2. We're going to talk about the energy of these systems, which is going to relate to the unit that we finished recently. And we're also going to jump back to the period calculations, which we also did when we were looking at circular motion. So lots of things from previous lessons are going to kind of come back to help us here today. All right. So a quick reminder about a few things with Hooke's law. Hooke's law has the traditional graph of putting the force of the pull or the force of the push, compressing or stretching a spring on the y-axis, and then measuring how much that force stretches or compresses the spring and putting that on the x-axis. And this is the lab that we did before, and when we graphed out that information, we were able to discover the slope of each of those lines. In this case, we're looking at 3 different springs, had a value, and let's see, Mark, what's the name for that K value that springs have? Hopefully you remembered, it's the spring constant. The stiffer the spring, the greater the value for K. And so we see 3 springs with 3 different spring constants. The weaker spring with the lower value, the stiffer spring with the greater value, and the other one kind of in between. So just a quick reminder about the lab we did earlier this year. These equations and these relationships are going to be really important for today's lesson. We also talked about Hooke's law in terms of Hooke's formula, and sometimes you see it as this spring constant that we just discussed is equal to the ratio of the pushing or pulling force divided by how much it's stretched. And sometimes you'll see a negative sign on it. If you're pulling with one direction, the spring will be exerting a force in the opposite direction, trying to restore itself. That's what we call it, a restorative force. So typically speaking, we're going to see it written this way. And the absolute values are so that you know you can use it when it's stretching or when it's compressing. It doesn't really matter the direction. While it is vector concept in terms of displacement and force, we're going to absolute value those because whether it's stretching or compressing won't change the mathematical results. And then all of the variables, the F of the S is the force of the spring, again in newtons. The spring constant is going to be newtons per meter, telling us the stiffness of the spring. And remember, the X value is not how long the spring is, it is how much it changed in its length. It's either compressed or stretched that much. And so remember, it is not the length, but the change in length. So 2-minute review on Hooke's law, the graphs that we produced, the formula that we used, and now let's see how it connects to Unit 7. In Unit 7, we're looking at simple harmonic motion, and like I said on that previous slide, the word oscillation is often thrown in here as a key vocabulary word. When something is oscillating, it's moving back and forth across some sort of equilibrium position. And you're hopefully going to see quite a few math relationships if you've learned about waves and equilibriums and sine functions, what they look like as graphs. That's going to come back. A lot of the same vocabulary you hopefully learned in math class around sine wave graphing is going to be used in this scenario as well. The other term is the equilibrium position. This is where the net force on the spring is 0. And we haven't learned about torque yet because I'm doing this in a little different order this year, but torque is something we're going to learn in Units 5 and 6. And so it is when the net force is 0, but also when the net torque is 0 on the object, that's where it's at equilibrium. It's going to be at the middle of those two extremes when something's oscillating back and forth. So let's visualize that. Remembering that a force of a spring is restorative. If we apply a force in one direction, it's going to apply a force in the other direction. And if we set it into oscillation, it will change in its force value and also change in its energy value. So if we watch this spring oscillating, the force gets larger as it approaches either amplitude or either extreme from the middle. But in the middle, it's got no forces exerted on it. The net force is 0 in that case because it's not being pushed or pulled right in that equilibrium position. So when we're thinking about this kind of a scenario, the net force is the force of the spring. And again, we call it a restorative force because the net force is always trying to pull it back to equilibrium, even in the midst of this oscillation or this vibration back and forth from one extreme to the other. The position where the object is in 0 displacement is where the net force will be 0. All right, so that equilibrium position is right there when it's not being pushed or pulled, right in the middle of the two extremes. Now, if we look at this kind of stage by stage as it's vibrating or oscillating back and forth, we can see that at the very extreme right, the force of the spring would be the most, therefore the acceleration would be the most based on Newton's second law. And then as it moves a little bit closer to equilibrium, the force decreases and the acceleration therefore would decrease again according to Newton's second law. When it reaches that equilibrium position right in the middle where the spring is relaxed at that instant, there is no force, there is no net force, and therefore there is no acceleration. As it passes that point and starts compressing the spring, the force would be pushing the other direction and creating an acceleration in that other direction. And as it continues to move to the left, the force of the compressed spring would be to the right, as would the growing acceleration. So hopefully you can see this pattern of at the extremes, maximum force and maximum acceleration, and at the midpoint, the equilibrium position, minimum force and 0 force actually, and 0 acceleration as well. Right, so that's going to be important for you to be able to think through, but we're not just going to think about how the force and the acceleration relates. We're also going to add something a little new to this. So on this graph, we're looking at the acceleration, but now we're, instead of force, looking at the displacement. So when we have a positive maximum displacement, the acceleration is in the opposite direction and also would be maximum. As the object moves towards equilibrium, the displacement is at this instant a little bit less, therefore the acceleration is less. When it reaches equilibrium, the displacement is 0. It is at the equilibrium position, is not stretched or compressed, therefore the acceleration is 0. As it starts to compress on the other side of the oscillation, we've got a displacement to the left and an acceleration to the right. And as we reach the maximum displacement to the left, we have a maximum displacement in the negative direction, but a maximum acceleration in the positive direction. Now, the reason that we're switching from forces to displacement is so we can actually define when something is in simple harmonic motion or not. And this isn't a frequently asked question on the exam, but it is something that shows up occasionally. And they seem to be adding a little more detail this year, so this is one of my early predictions. I suspect there might be a bit more on this unit compared to previous years, because they are adding some detail into the curriculum guide now. So I think it's probably good if you understand what we mean mathematically when we say simple harmonic motion, or SHM. If the relationship between acceleration A and its displacement x is proportional, so in other words, the acceleration is proportional to the displacement but in opposite directions, that is when we call its oscillation as simple harmonic motion. So let's take this definition, this acceleration is proportional to the displacement but opposite in direction. Let's take that and see if we can derive some relationships. You guys always like deriving equations, so as often we're going to start with Newton's second law. And if we think about the net force for a spring is going to be based on Hooke's law that we reviewed just a few minutes ago. And so we've got negative kx because a spring is what we're looking at. The spring is causing the oscillation of the object. And so the net force is the spring constant times the x. It is the opposite direction to the applied force. And so we've got this mass times acceleration. The displacement and acceleration are going to be in opposite directions. Now, if we just algebraically solve this for A, we're just going to divide both sides by m. I've written it the other direction so that A is on the left, but all we're really doing is dividing both sides by m here. Now we have a formula for acceleration that is related to the displacement x. And so if we think about that definition for simple harmonic motion, if it's oscillating and it's at the end and it has simple harmonic motion, then we should see, like we said, the acceleration should be directly proportional to that displacement, but opposite in direction. Well, if we think about that, that means that the acceleration must be equal to some constant multiplied by the displacement in the opposite direction. And the spring constant is constant by its very name. We're reminded of that. And the mass of the object wouldn't be changing, so the mass would also be constant. So this k over m value that we see here is a constant value, thus showing us that if the spring is behaving as an ideal spring and obeying Hooke's law, it does have simple harmonic motion because the acceleration will be equal to the constant, in this case k over m, times the displacement, which is in the opposite direction of the acceleration. So that's just a quick showing of how we define simple harmonic motion and how it connects mathematically to Newton's second law and Hooke's law, combining those two things together, along with the third idea of what simple harmonic motion is, and showing that springs obeying Hooke's law are going to be in simple harmonic motion. All right, let's continue. So simple harmonic motion and an object that's moving in a constant velocity in a circle, which is uniform circular motion that I mentioned a little bit ago, have a lot of things in common. So an object that oscillates with simple harmonic motion has a motion that is identical to the y-axis motion of a point or an object that's moving with a constant speed in a circle. So let's visualize that. As we watch this dot moving in a uniform circular motion, meaning it's moving in a circle, the radius is constant, and the speed is constant, or the magnitude of the velocity is constant. The direction of the velocity is constantly changing. That's why there is a centripetal force, because if the direction is changing, that means that part of the velocity is changing, which means there has to be an acceleration, which means there has to be a force. And the net force would be the centripetal force. But this is just a quick review there of those keywords about centripetal force. But let's just watch the y position as this object moves in a circle. It's at its minimum, it's at its maximum, it's at its minimum, and then it revolves back to its maximum again. This hopefully is resembling the process that you maybe learned in your math classes about the shape of a sine or cosine graph, this sine wave, where it's reaching maximum and minimum. We got our crests and our troughs, and we're going to add some vocabulary to this. So this is a clear connection between circular motion and something that's moving in simple harmonic motion. We're going to keep revisiting this sine connection and some of the key words. So let's see, Jonathan, if you've learned this in math class at this point, what do we call the maximum, the distance that is related to the maximum height of this curve? Or we could also say the distance that relates to the maximum depth of this sine curve. What do we call that height or depth from the midpoint? Hopefully you got it, or maybe if not, if you didn't remember it or haven't learned it yet, maybe someone helped you out. It is called the amplitude. And when we have something moving in simple harmonic motion, like an object attached to a spring, we call those maximum limits that it's stretching to or compressing to its amplitude, just like we call the maximum peak and the bottom trough distance from equilibrium or from the midpoint the amplitude. So if you've learned that term amplitude in terms of sine waves, we're using it the same way here. It's the maximum to the right and the maximum to the left in this simulation. And so amplitude is going to be a common word, hopefully. And just like on the sine graph, we have this equilibrium that passes right through the middle of the sine wave. We also have an equilibrium position in this oscillation, where we are not at any extreme, we're actually in the exact middle. So the amplitude is the magnitude of the maximum displacement of the object from its equilibrium position when it's in simple harmonic motion. Just like the amplitude is the maximum distance from the equilibrium position in a sine curve. So there's a good relationship there that hopefully connects some math and some physics in your brains. All right, next up, let's shift to energy. We've learned in our unit about energy what the potential energy of an ideal spring is. We've learned this equation, the EPE, or the U sub S. EPE is how a lot of students like to write it, elastic potential energy. College Board writes it, U for potential energy, S for spring, is equal to 1/2 K times X squared, where K is the spring constant, still in newtons per meter, and X is still the spring's extension or compression, not its length, but how much it changes in length. The more it changes, the more energy it will store, and the more work you would have to do on that. I also hope you can recall back to our Hooke's Law lab. We talked briefly, and we've revisited this since when we went to our unit on energy, that when we graph the force on the y and the displacement on the x for a spring, Not only does the slope tell us the spring constant, like we reviewed a few minutes ago, the area under the curve, and here's the deriving process we did a while back, actually comes up with the amount of work done, force times displacement, and that work done is how much energy is stored potentially in the spring. And so this 1/2 kx squared relates to the graphical relationship of force and extension or compression of a spring. So a couple of reminders there. And one other reminder, the formula only applies to ideal springs, ones that obey Hooke's law, which they very seldom are ever going to ask you about something that doesn't obey Hooke's law. But that is something to keep in mind. All right, let's view this potential energy and the transformations as the oscillation occurs. So here we're back to our mass on a spring being oscillated back and forth. At this point, it's fully compressed, so it has maximum potential energy, maximum elastic potential. Its velocity would be 0. The K, in terms of kinetic energy, now that we're not looking at lowercase k with the spring constant, but kinetic energy is 0 because there's no velocity. The X, or compression, is maximized. Therefore, the potential energy of the spring is maximized. Now, when it reaches the midpoint, as we watch it oscillate, it's going to have maximum velocity because that's when it's moving the fastest. As it moves past that to the right, it's slowing down as the spring stretches. And as it moves past that to the left, it's slowing down as it compresses. But right there, it would have maximum speed, maximum velocity, and therefore maximum kinetic energy. But it's not stretched at all. So it would have no displacement and therefore no potential energy in the spring. And then when we reach the far right, it again comes to rest at that maximum amplitude. So no velocity, therefore no kinetic energy. And the displacement will be maximum to the right from the equilibrium position. Therefore, it will again have the maximum elastic potential energy. And you notice that just like we saw in the skateboard parks illustrations, the kinetic and potential energies are oscillating, but the total stays constant as long as there is no internal or dissipated energy. So there's no friction, no loss, no air resistance. We're assuming perfect conditions here. No work is being done externally on this system. Now, if you imagine this, and let's go back a little bit to that sine wave view and think about this energy. We've got the kinetic energy rising when the potential energy falls and vice versa. But if you add those two sine waves together, they give you a straight line with a total energy of the kinetic energy summed up with the potential energy of the spring. And so that's what we're seeing. That's what we're seeing here with a bar graph oscillating back and forth. We can also represent it with line graphs showing that transition of kinetic energy above and below, or up and down, and the potential energy up and down. We can't have negative energy because energy is a scalar. There are times we talk about energy leaving a system or entering a system, and we sometimes use positive and negatives to indicate that. But this being a closed system, they're always going to add up to some positive net value or total value. And so we're drawing both of these curves above the 0 line to show that kinetic energy, when it reaches 0, is going to show the potential energy at its max and vice versa. All right, so another connection between simple harmonic motion and uniform circular motion. We saw it before looking at the sine wave, but now I want you to see it again looking at that energy fluctuation. So springs and waves behave very similar to objects that move in circles. The radius of the circle is symbolic of the displacement x of a spring or the amplitude a of a wave. And so we can see this circular motion matches the oscillation. This time we're looking at a horizontal oscillation and the horizontal displacement of the object in circular motion. And then down below we're seeing how when the spring reaches maximum extension and maximum compression, we've got lots of elastic potential energy. And when it's at the equilibrium point, it has lots of kinetic energy. And so again, here as we look at these values, the x of the spring is on both of these graphs, both of these relationships. The a of the wave, the amplitude, we can see is changing, reaching maximum amplitudes, both above and below. And the radius of the circle is going to be shown how it connects to the uniform circular motion. There's yet another connection. So we've seen how it connects you to a sine wave. We've seen now how it connects to the energy. There's two other terms we learned when we were learning uniform circular motion that this also closely connects to. And they are t for period, time taken for one oscillation, and so that'll be measured in seconds, and lowercase f for frequency, the number of oscillations that take place in 1 second. And while period is measured in hertz, a period is measured in seconds, frequency is measured in per seconds, which we usually write as hertz. So let's see. Caleb, how do period and frequency relate mathematically? Are they directly proportional, inversely proportional? What you got for me? Hopefully you recalled that they are inversely proportional. If not, maybe someone helped you out, or I'm sure there are other people that didn't remember as well, but let's review that. If we have something moving in uniform circular motion, the period would just be how long it takes for a full cycle. And so in this case, it's moving at a rate that finishes the circle in 2 seconds. And since frequency is reciprocal to that, it would be 1 over 2 seconds or 1/2 hertz, 1/2 per seconds, because seconds is in the denominator now that we've reciprocaled it. All right, and then if we look at this scenario, moving faster, if the period is 1 second, Julia, what is the frequency? Hopefully you got the reciprocal of 1 is also 1, so it's taking 1 cycle per second, or 1 hertz. And then if we speed it up even more, and now the period is 1/2 of a second. Alex, what would be the frequency? The reciprocal is 2 hertz, so hopefully you got that right. And then for the last one, moving even faster, the period is 1/4 of a second. And so, Dia, what is the frequency for this one? Hopefully you came up with 4 hertz. So we've got this reciprocal nature of frequency and period. That's true when we think about those terms with uniform circular motion. That is also true when we think about oscillations. So when a spring makes a full a spring makes a full stretch and compression cycle, that would be, the time it takes would be its period, and the number of cycles per second would be its frequency. There's another kind of motion we haven't really looked at yet in this unit, but we have looked at it before earlier this year, and that is a period of a pendulum. We actually did a lab with this at the beginning of the year, and primarily we were learning how to evaluate relationships mathematically and what things were linear and what things were not linear and how we identified nonlinear relationships. And we sort of derived this equation from our graph, from our data in that lab back in August or September. But here it is again. This one is on the formula sheet, nothing you have to memorize, but the period of a pendulum, T for period, in seconds, is equal to 2 times pi. Again, you can see some relationship to that circular motion with this 2 pi relationship, remembering that a full cycle is 2 pi radians. And then that is multiplied by the radical, or the square root of the length divided by the value for g, the acceleration due to gravity, or you could call it the field strength of gravity. All right, so that's our relationship. Now note, we also learned back when we were doing that lab, the mass of the pendulum had nothing to do with the period. We've proved with our data we got a straight horizontal line, no relationship. And the amplitude, how far we stretch it, within limits, and we'll come back to that here in a few minutes. As long as we don't lift it too high, then we also don't have any effect by the amplitude. And after the lab, I did show you a very complicated equation that at more advanced levels of physics you might see, where we account for larger displacements from hanging. So if we drop it from a very high angle, we start to have to make some mathematical calculation adjustments. But as long as we're dropping it from a reasonably small angle, 35 degrees or less is always going to give you pretty reasonable results. The angle doesn't matter, the mass doesn't matter, but the length of the pendulum definitely does, and so does gravity. Although, since we don't usually go to other locations where the acceleration due to gravity is significantly changing, seldom do we ever have to factor that in for pendulum. So as we said, this formula does become less accurate the larger the amplitude, or in other words, the larger that angle is that we drop it from. So we do want to keep that in mind. All right, so let's review a little bit, summarizing some things here, using some words that we've just reviewed. So with a pendulum, it would be an example of simple harmonic motion, swinging back and forth at a rhythmic pattern. And if we're ignoring air resistance and friction, if we can eliminate those external forces, this would just keep swinging back and forth in simple harmonic motion. And the amplitude would be that angle that we pulled it to the side from equilibrium. And we would typically want to measure it in radians, but it could be measured other ways. But generally speaking, for a pendulum, radians is going to be our best bet. For the period, then, it's the amount of time to complete one cycle, so all the way over and all the way back. It's not just from side 1 to side 2, but side 1 to side 2 and back to side 1. That's the full cycle. So the number of seconds it takes to complete that is the period, again, capital T as our variable. And then frequency, the reciprocal of period, lowercase f, is the number of cycles that are completed in a unit of time, usually per seconds, which we often write as hertz. So just reviewing the way those three vocabulary words connect to the pendulum lab that we did months ago, and we need to keep reviewing now that we're focusing on it as a source of simple harmonic motion. Now let's compare pendulum versus a spring pendulum or a spring oscillation. So on the left, we've got the traditional hanging pendulum. We can see its maximum displacement and its minimum displacement at equilibrium. And then we've got its maximum displacement to the other side and then back to equilibrium. On the spring side, we've also seen this multiple times now. It's got a maximum displacement or a maximum amplitude where it would have maximum force and maximum acceleration, but zero velocity. And just like when the pendulum is at equilibrium, it would have the maximum velocity there. The spring, when it's at equilibrium, also has maximum velocity, and so it's got maximum kinetic energy. And just like the pendulum swings to the other side and achieves its maximum displacement or maximum amplitude again, the box would compress the spring and create the maximum force, maximum acceleration, but at that maximum, it would come to rest again. So there would be no kinetic energy at that extreme left. And then back just oscillating the other way, it reaches equilibrium, no force, no acceleration, but maximum speed, so maximum kinetic energy. And then all the way back over as its full cycle back to where it started, its maximum force, or sorry, its maximum displacement is where there is maximum force and maximum acceleration, but zero velocity. So we can see zero kinetic energy at the amplitudes, maximum kinetic energy at the midpoints or equilibrium points, which is true for both pendulums and for springs or masses on a spring. All right. So now we've talked a little bit about pendulums. We've connected it to mass on a spring. Now let's look at the period of an ideal spring's equation. This is what you're going to be needing to focus in on for our lab that we'll be starting soon. So T is period of an ideal spring, and the equation for the period of a spring is 2 pi, again, in relationship to that circular motion. But this time it's not the length, it's the mass of the bob. So in a pendulum, the mass didn't matter, but for a spring that's oscillating a mass, it does. And before we worried about gravity as providing that acceleration, but here we're thinking about how tight is that spring? What is the spring constant? And so we have a little bit different relationship that's more appropriate and applicable to a spring scenario. So notice again, G that we saw in the pendulum relationship, not existent here. The acceleration due to gravity is going to be equal the whole time, and so there's no kind of angled force of gravity because it's staying vertical, or if it's horizontal, then we're usually doing it on a frictionless tabletop and there is no vertical force at all. Amplitude also doesn't matter, so the farther we pull it, the more force it requires, and the more energy we would be storing in it because we're doing more work on it, but it wouldn't affect the period. And that's because if we pull it further down, for instance, when it reaches its maximum velocity, it's going to be moving much faster because it's got a greater acceleration at its maximum stretch. And so while it's got a greater distance to cover, it's going to be moving faster at its maximum velocity. And so hopefully that kind of makes sense. And again, just that same reminder that we've seen a few times, this formula does only apply if the spring is obeying Hooke's law. In other words, it's behaving ideally. So seldom do they ever ask you questions when it's not, but they sometimes use that phrasing. So I like to bring it up a few times so that if you see the words ideal spring or obeying Hooke's law, it doesn't throw you off, but it's something you've seen multiple times and are comfortable reading. All right, on your whiteboards, let's do some math. So slingshot example. A slingshot is made of a light leather cup attached to 2 rubber bands. It takes a force of 30 newtons to stretch the bands 1 centimeter. Part A, what is the spring constant of the bands? All right, so on your whiteboards, see if you can calculate the spring constant of the bands. Right? Hopefully I've given you enough time to process it there. It's a little harder when I'm not there to ask you to raise your hands, but in part A, we're just using Hooke's law. The spring force is equal to the spring constant times its displacement. We know the force, we know the displacement. You do have to make sure you change this centimeters to meters because the units for spring constant are traditionally given in newtons per meter. That's because we want it to be more closely related to the newtons times meters when we look at joules and all those other things when we're talking about energy. So we do want to make sure we churn this displacement to meters, little note there. Part B, what is the potential energy stored in the bands when a 50-gram stone is placed in the cup and pulled back 0.2 meters from the equilibrium position? So try solving part B on your whiteboards. All right, hopefully that was enough time. You're using the potential energy of a spring. We found the K value on part A, and the potential energy of a spring is 1/2 K times x squared. We've seen the displacement is 0.2 meters. We do need to remember to square that according to the equation, and we should get 60 joules. And then part C, with what speed does the stone leave the slingshot? You're having trouble getting started, this might help you. The potential energy of the spring that you stored in it should equal the kinetic energy that the stone leaves the spring or leaves the slingshot with. When the cup reaches equilibrium, it's going to start slowing down, and the rock will not. And so at equilibrium is when the rock should be released from the cup on the slingshot. Right. You hopefully figured out that the relationship would be 1/2 kx squared for the potential energy equals 1/2 mv squared. If we were starting from scratch, you might notice the 1/2s cancel and simplify the relationship. But since we already know what the U sub S, the elastic potential energy is, we might as well just substitute that in for the 1/2 kx squared as 60 joules. And then we know the mass of the stone is 50 grams. We do have to switch it to kilograms, so dividing by 1,000. So we've got our 60 joules of potential energy stored in the slingshot equals 1/2 times the 0.050 kilogram stone multiplied by its velocity squared. And so at that point, it's just algebra. And so that velocity would end up being 49 meters per second. So if you have questions on any of these steps, jot them down in your notes. And then when I'm back in class on Thursday, we'll take a few minutes to see if you have any questions on any of these, and I can open them back up and talk through it with you if you need it. The main thing we'll be doing Thursday is our lab. It's going to be, again, an abbreviated lab because we're coming right up on the break, so I'm not going to ask you to do a big report, but I am going to ask you to gather some data and do some analysis of the energy and more have like some conversations about it versus doing a ton of graphing or a big lab report. But that'll be Wednesday, because we're switched our odd and even this week. All right, next question. Spring pendulum example. So sometimes they do call this oscillating spring system a spring pendulum. Sometimes they call it mass on a spring. And so those are probably the two most common phrases you'll see. In this case, it was just a slingshot, so you're all familiar with what that looks like. Here they could call it mass on a spring or spring pendulum, but it says a 200-gram mass is attached to a spring and it executes simple harmonic motion with a period of 0.25 seconds. If the total energy of the system is 2 joules, find A, the spring constant of the spring, and B, the amplitude of the motion. So I'm going to give you a little time to solve A, and then we'll check that. If you finish with part A before I call you back to attention, you can go ahead and start part B. All right, so if we're given the period, that's a pretty good hint. We're going to want to use the period equation we just learned. And so if we plug that equation in, the period of a spring is 2 pi times root m over k. The period was given, 0.25 seconds. 2 pi is constant. The mass is 0.2 kilograms. And the k is what we're solving for. This takes a little bit trickier math. So we've got to take the 0.25 divided by 2 pi and then square both sides. And then I would suggest just cross multiplying so the k is out of the denominator and taking your 0.2 divided by whatever you got when you squared the other side of the equation. And if anybody has an answer, say it out loud. Hopefully, somebody said 130 newtons per meter. That is our K value. Now let me give you a few more minutes. Find the amplitude of the motion. And I'll give you a little hint. Amplitude would be the same as how much the spring got stretched or compressed. All right, so this is an energy question. We were told it has 2 joules of energy, and so that would be the elastic potential energy when it's fully stretched, and that would turn into energy kinetic when it's launched, or when it's at the equilibrium position. But we know the 2 joules is the elastic potential energy, 1/2 is a constant. K is what we just found in part A, 130 newtons per meter, and so we're solving for A. So we would need to multiply 2 by 2, divide by the K value, square root both sides, and if you got an answer, say it out loud. All right, hopefully some of you were saying 0.18 meters, 18 centimeters. All right, again, if you have questions on this one, any of the steps, jot it down in your notes. Remind me tomorrow in class. Or not tomorrow, but Wednesday in class. Well, I guess it is tomorrow for you when you're seeing this video. All right, next question. Swinging pendulum. All right, now this is an interesting example. We have a visitor to a lighthouse wishes to determine the height of the tower. She ties a spool of thread to a small rock to make a simple pendulum, which she hangs down the center of a spiral staircase in the tower. I don't know who walks around with spools of thread in their pocket, but apparently this person does. The period of oscillation is 9.40 seconds. What is the height of the tower? All right, so again, you've got a reference to period, which is your strong hint. You're going to need to think about the period of a pendulum. So work on that one on your whiteboard for a couple minutes. If you haven't finished it yet, hopefully you've at least set it up. Using the period of a pendulum equation, we've got 2 pi times root L over G. L would be the height, since that's the length of the string. And so we need to solve for L. They're showing you the algebra first, which is a good thing to try to do. It's good skill for developing your ability to derive equations. So they would square everything first, which you don't have to do. You could divide by 2 pi first and then square it, but they're just squaring everything first. And so you get the period squared. You have to square the 2, which becomes 4. The pi is squared, and then the root is gone, and we just have L over G. And now we need to solve it for L, so we're going to cross multiply the G and divide both sides by the 4 pi squared. So we get the period squared times G over 4 times pi squared. And so we were given the period of 9.4 seconds. We know G is just 9.8, or you could use 10 here as well. 4 is what came out of the equation from the 2 pi portion, and then we just need the pi squared. And you can use the pi button, you can use 3.14. Either of those would be sufficient. And then if you have had a chance to calculate this answer, say it out loud. All right. Hopefully you got the length would be the height of the tower, and that would be 21.9 meters. If you have questions, jot them down in your notes. Ask about it on Wednesday. All right. Last little bit to wrap up. The energy of a mass spring system is kind of looking at it in the different places graphically, equation-wise, all the different forces. One of the most common questions in the exam is the energy of a mass on a spring. And so when it is all the way compressed, it has no velocity and it has maximum potential energy, which we see down here by the red dot. Lots of EPE, 0 KE. But the total energy, the red line across the top of the graph, stays consistent. And then when it's at the midpoint, now if we think about the total energy, it's all motion. The spring is relaxed. There is no force on the spring. There is no stretching or compressing at that point. And so it's all kinetic energy, 1/2 mv squared. And therefore we see on the graph maximum kinetic energy and 0 elastic potential energy, but the total still being constant. And then when it switches to the other amplitude, the other extreme, again, we see the total stays constant, and now we're back to having maximum elastic potential energy and 0 velocity, therefore 0 kinetic energy. So just again, a quick review of how all this pieces together. Now on Wednesday, we'll be doing a spring pendulum lab where you'll be hanging a weight from a spring, and you'll be measuring the mass, and you'll be also measuring the period. And so you're going to be doing some graphical analysis. You're not going to have to, like I said, print a bunch of graphs and do a bunch of reports with it, but I do want you to get your data and graph it, and I'll explain more of that at the beginning of the period on Wednesday and give you a handout to complete. But that'll be your process for the spring pendulum lab. So if you have some time left, I think we're just about out of time, but you could go ahead and put spring pendulum lab in the table of contents in your journal. You go ahead and set up your first page with the date, which will be Wednesday's date, and the title, and make sure your page numbers are caught up and you can get that taken care of. Otherwise, I look forward to seeing you on Wednesday. Sorry I couldn't be there today. Hopefully this was helpful getting us started in Unit 7. And like I said, hope you have a great rest of your day.